All right, I should be recording. Good evening, everyone, and we're back for another discussion on Aspen one-liner. We'll jump right into it because I want to make sure we get through everything. We're going to start with how we run faults. So before we start running faults, the first thing we want to do is look at the faults options window. That's the window that kind of selects all of the criteria that you may want to adjust for how the fault is run, what assumptions are made when Aspen one-liner runs the fault. So like we talked about, usually you do from a linear network solution. You also have the option to do an assumed flat per unit voltage. So the assumption would be like every bus was at 1 per unit when the fault happened. And obviously the pre-fault voltage will impact the amount of fault current that there is. Usually you do the linear network solution unless you're checking like breaker ratings. They're also used for some regulatory bodies like to have certain criteria selected here, like ISO New England likes to do an assumed flat per unit voltage of 1.05 for CMP's territory. And that's really what a lot of these options are for. And it's because they want to have the faults modeled the same way that they used in their PSSE short circuit programs for when they do their system stability studies. So that's what they call the classical fault assumptions. So most of the time you're going to do from a linear network solution. That's what Aspen one-liner recommends that you do, but they provide these options so that you can simulate those classical fault assumptions. The generator impedance, this will depend on what you're looking for as far as if you've got a generator that's at or near your local bus and you're looking for your maximum fault current, well, you'd want to use the subtransient impedance for the generator. But if you have a time over current relay that's going to operate on the order of seconds, then you might want to change that to your synchronous impedance. So this is where you would do that. Defining the fault MVA as a product of current and pre-fault voltage, this doesn't make any difference to the fault calculations. All that's going to do is in the TTY window where it gives you your MVA fault availability, it's just going to change how that's calculated. So that's not a big deal. Ignore mutuals under this threshold. That's if you want to ignore the impact of mutual coupling impedances on your faults. You usually wouldn't do that. Ignoring loads, again, you wouldn't normally ignore any of this stuff. The loads typically aren't even modeled in North America, so that doesn't really make an impact. Ignoring the transmission line conductance and susceptance. Again, normally don't do that, but ISO New England wants you to do that. Shunts, that's ignoring the impact of capacitors and reactors. Or the transformer line shunts. I've never even seen a model with a transformer line shunt in it, so these really don't matter much. The MOV protected series capacitor. If you have a series compensated line, which is a line with a capacitor in it, and they put the capacitor in there to decrease the reactance of the transmission line, and that allows them to push more power down the transmission line. There are 2 of them in Maine that I'm aware of, and they're on 345 kV lines that interconnect between CMP and Versant. Those are the only 2 I'm aware of. But if they're often protected by MOV or metal oxide varistor, that if the current through the capacitor gets too high, you generate a voltage across that capacitor, and the MOV is directly in parallel with the capacitor, and it detects that voltage being too high, and then it'll short out the capacitor so that the current goes around the capacitor and it protects your series capacitor. So if you, for some reason, are in a model where you have to worry about this, you can enable this and look at whether or not the capacitor is protected by the metal oxide varistor. And then this acceleration factor, I assume you'd have to play around with that. I've never done line protection for a series compensated line, but Aspen has a paper that they cite here where they the paper recommends a convergence factor so that the reaction of the metal oxide varistor is nonlinear. So Aspen one-liner doesn't do a good job of modeling it. So they just iterate the fault multiple times, and they use this acceleration factor to adjust how quickly the solutions converge. So the Aspen default is 0.4. The paper that they cite suggests a convergence factor between 0.5 and 0.7. Again, I don't think you'll ever have to worry about this, but if you did, that's what that's talking about. Current limited generators, we talked about this last class. If you have some current limited generators in your system, and we put in the current limits to represent different scenarios, short-term faults versus continuous faults, that is where you would, that's where you would select that. So you can either ignore the current limits and it'll act just like a normal generator, or you can enforce the current limits of A or current limits of B so that you can see the reaction of your generators under those scenarios. Again, normally you'll just ignore current limits. And then we talked about this too when we talked about the type 3 machines and the type 4 machines. If you want to simulate the converter interface resources and the type 3 wind plants, these are the options to do that. So you'll usually want to have those on, and you can't have these on if you do an assumed flat pre-fault voltage. So just be aware of that. And then simulating current controlled, voltage controlled current sources, excuse me. This is where you turn that on if you wanted. So that's kind of the fault preferences. So you want to set this up before you start doing your coordination study or fault analysis, because if this is out of whack, your results aren't going to be helpful. So you want to do this first, and this is, the preferences are saved with the one-liner model. So you kind of want to check them beforehand because you don't know what somebody else might have been doing with the one-liner model before it got to you. So always good practice to check those before you start running faults. All right, so now let's run some faults. So they're classical faults are the most common, and that's what we're primarily going to be talking about. There are also stepped event analysis. That's a really cool tool, but we're not going to have time to get into that, I don't think. So, but you'll run if you use the software regularly, you'll run a lot of classical faults. So what you can do is you can right click on a bus or use the hotkey of S and specify a classical fault, and it'll bring up this window. And here you can select the different kinds of faults that you run. 3-line to ground, double line to ground, single line to ground, line to line. And then you can even select which phases that you want to fault when you run the fault. Typically, you don't have to worry about this. The only reason that this might be useful is if you're trying to recreate a fault that happened in real life, and you might want to actually get, say it was a C to A fault, you want to run that so that your results will match your event report. So this is helpful for analyzing event records and things like that. But other than that, you can just use the defaults. And you might wonder why you do an A fault and then a B to C fault for line-to-line faults. That's just kind of a typical practice. And the reason you do that is if you're generating faults to be used for relay testing, it's good practice to get all three phases to make sure that all three phases of the relay are being tested. So it's just kind of a good practice industry standard to use A for single line of ground faults and then B to C for phase-to-phase faults. So when we run this, these little tick boxes mean that it's going to run that fault. So if we stopped here and just said simulate, it would run a 3 line to ground, double line to ground, single line to ground, line to line fault here, and they would run it without an outage. If you also clicked this box, you can click either or both. It'll run them with an outage. Okay, I guess I should talk about the fault Z too. So if you want to add impedance to the fault, you can do that here. So you can add resistance or reactance to the fault manually. You can also enter like steps, and there's a little explanation on how to do that here. If you want to like add resistance in steps of half a ohm or whatever, you know, half, 1 ohm, 1.5, you can do that. You just leave it 0 typically for a bolted fault. So because we are selecting this no with outage tick box, and we hit simulate, now it'll give us this new box that allows us to select the branch outage. Okay, so and these options are also going to stack. So we're kind of getting, you know, an exponential increase in the number of faults we're going to run. So we can run this fault with outages. Oh, I guess I should describe what this means. So I don't really like the way that these are listed here. I don't think it's intuitive, but so you know, this number represents the bus number. So I told you that it doesn't really matter what bus number you give it, and it doesn't, but that's where that number comes from. So maybe your system is really well organized and you know exactly what bus number every bus is. If that's the case, good for you. But in my experience, that number ends up being arbitrary. But that's what that number is. That's the bus number. And then this is the name of the bus and the voltage. And the reason it gives you both is because you may have 2 buses at the same substation. You want to call them both Florida, as in this case. So, or excuse me, like Arizona here. Arizona's got a 33 kV bus and a 132 kV bus. So they're both called Arizona. So they put the voltage there so that you can distinguish between the 2 buses. So this is between 9 Arizona 33 kV and whatever element is connected between that bus and Florida 33 kV, which we know is over there. The next one, this is the circuit ID for that particular element. We know this is a line, and that's what that L means. So this is the line that goes between Arizona and Florida. So if we come over here, the circuit ID is this number. This is automatically generated. So if we had another line that was parallel to these 2 that connected the same buses, just put in a new line, sure. Now we have 2 lines. When we go back there, it'll say line 1 and line 2. So it automatically incremented that. And that's so that the lines or the elements always have a unique name so that Aspen one-liner knows what you're trying to do. But how would you know which line is which? Well, the reason you couldn't really tell without going and clicking on it is because these lines aren't named. But if you do have a name for the line, let's say we call this one test and this one I don't know, test 2, sure. Now when you run the fault, it'll actually list the name here. Okay, so now you can, like, if you know which one's which, now it's easier to distinguish between the 2. So that's why having the names is good, but it's not absolutely necessary. The number of tiers is the number of buses away you want to consider. So 0 would be only elements that are connected to that bus. If we increase that to 2, it'll give us all the elements that are 1 bus away. So it'll add, these 2 lines and the 2 lines that are connected at the Arizona 132 kV bus. So you can increase this to try and take outages that are further away from the bus you've selected. Ordering by tier just orders them from closest to furthest away. The find text is helpful because if you did want to find, well, hey, where's that test 2 line? You can type that in here and now it'll highlight it. And that's helpful because this structure is not very helpful in my opinion. So it's nice to be able to find the text and find the line you're looking for, the transformer or whatever. Then you can select whether you want to run the faults the outages, the faults with the outages 1 at a time, 2 at a time, or all at once. And you can't do 1 and 2 at a time and all at once, but you can do 1 and 2 at a time. And so say we add like these 4 contingencies, these 4 outages to our fault list. What it'll do is it'll run a 3 line to ground fault with test out of service, and then it'll run a 3 line to ground fault with test 2 out of service, and then it'll run it with this transformer out, and then this line out, and then it'll also run double line to ground, and you can see how these are all stacking up. And especially if you do 2 at a time, because now it's going to run it with test and test 2 out, and it's going to run it with test and this transformer out, and test in this line. Yeah, you get it. So you can run a lot of faults very quickly. The option to ground the outaged lines at both ends, usually you wouldn't select that because the reason a line is typically out is because of a prior outage, right? The breakers have opened and the line is out. The reason you would do this is if the line is out of service for maintenance purposes or construction purposes. If they were going to be working on the line, a lot of times they'll open the line up and then have switches that are visually open so that they know that the line is de-energized, and then they'll hang grounds on each phase, ground conductors from each phase to ground, so that it's clear to the people working on the line that the line is dead. So you'll hear the term working between grounds. That's what they're saying, is that there's a ground over there and there's a ground over here, and we've got to stay between those so that we know that that the equipment is dead. And then if somebody were to accidentally energize the line, hopefully the fault current goes into the ground instead of a person. Why would you want to simulate that? Well, that goes back to the mutual coupling between transmission lines. So you can imagine if the line is just open and you have a fault on a single line to ground fault on a line, if the parallel line is just open, then there's no path for the 0 sequence current that's now coupled onto that line. There's no path for that current to flow to ground except through the phase to ground susceptance. But if the line is the parallel line is grounded on both ends, now you've got a very low path to ground. So that can increase the amount of increase or decrease, depending on the orientation of the lines, the amount of fault current on the line you're looking at. So you may want to do that to check a ground instantaneous element or ground zone 1 element to make sure that even if the parallel line is out and grounded, that you're still not going to operate for whatever fault. Normally you don't have to worry about that, but that's what it's for. And then again, you can add an impedance value to the line that's grounded on both ends. Okay, so let's run that. And so what we've just done is run, I don't know how many faults that is. I guess we can look right here. So this button allows you to view all of the faults you've just run. So we ran 44 faults with those selections, and it says what the fault is, what's out, what type of fault it is. So you can use this if you ran a bunch of faults to try and find the one you want to look at. I don't use that too much. What I typically do is I'll run the faults and then I'll use this button to go to the first fault, and then I'll just start scrolling through. And you can usually tell, well, you can look down here and tell for sure, right? This is a bus fault on 9 Arizona, 33 kV, and it's 3 line to ground with outages. And you can see what's out with these red X's, and it shows it disconnected from each bus. So this is a 3 line ground fault on this bus with this test line out of service. Okay, and then you can start scrolling through. And you'll see over here that these buttons, I don't know if you can tell on the video or not, but these buttons are kind of like jumping around as to what's selected. And the reason it's doing that is it's showing the most relevant current for the fault that you ran. So let's say a 3 line to ground fault, we know that all phase currents are going to be of equal magnitude, and they're going to be 120 degrees out of phase with each other. Because, well, we know that. So what it's doing is it's showing this plus stands for the positive sequence current. Okay, so all these values are positive sequence current, and you can tell that because there's a little P here that stands for positive. So the way you would read this is the fault has 6,190 amps of fault current, positive sequence at an angle of negative 77 degrees. Okay, and then these black numbers are the branch currents. Okay, so if I grab this, you can see that moves with it, or I can move the branch current around. And if you select just the current value, it'll show you which branch it's representing. And the reason that is because these can get kind of jumbled if you've got buses that are too close together. It's like, well, which one's which? So they help you distinguish that by highlighting the element it's for. Okay, so if you had a relay here, that relay would actually see the 3,227 amps of positive sequence current, but you can see that the total fault current is 6,190 amps. So if you added these 3 currents together, the vector summation would equal 6,190 amps. Okay, I'm going to delete this out of here because it's getting in my way. And it wasn't there originally. So hopefully that's clear. Okay. More often than just running bus faults, you'll want to run faults relative to a relay group. And what I mean by that is you'll want to see how these relays operate for faults on a line usually, or not necessarily on the bus. You'll want to see what happens if like in the case of this transformer, you'll want to see what happens if the fault is between the relay group, whether it's a breaker or a fuse, and the transformer, right? So more often than bus faults, you run line faults. So you can select a relay group. You can do it here too, but usually you'll have relay groups for any line fault you might want to run. And you can do the same thing, specify classical fault. Now we've got a few new options. Now you can do a close-in fault, okay? So that's a fault with 0 impedance. It'd be like right on the breaker bushings between the relay group and where the fault is. So it's right there on the terminals with no impedance. So if we ran a bus fault here, for instance, 3 line to ground, bus fault, with no outage, it's going to be 3,910 amps of fault current. If I ran it close in, it should be the same. It's just changing that location. See that? Okay. So that's a close-in fault. A close-in fault with the end open would run the same fault, but it would run it with this terminal open. Okay. And the reason you might want to do that is if the fault is like towards this end of the line, you're expecting that relay to operate pretty quickly. So you might want to run it assuming that that terminal opens. So you can run, well, that's why you do it. So you can also run a remote bus fault, which will just put a fault on the other end of the line at that bus. Okay, that's a remote bus fault. The line end fault will run, it's similar to the close end fault with end open, but it puts it at the other end of the line with the end open. So that's used quite a bit. Again, the reason you do that is if the fault is close to this breaker or relay group, where you're assuming that that's going to open and open quickly. And we want to see what this relay does when that terminal opens. Okay, because this is probably going to be on a time delay for a fault at the very end of the line. Then there's the intermediate fault. So what this does is you can put a fault at different percentages of the line. So we can do 50% of the line, and now it'll run it right in the middle, and it kind of shows that pictorially here by putting it halfway, half the length of the line. So that's an intermediate fault. And then this auto sequence check mark, I use this all the time. What this will do is it'll put a series of faults in steps of this percentage from 0% of the line to 100% of the line, and you can change these, right? So if we just do 2% steps for the whole line impedance, it'll run, you know, those 50 faults, right? Starting right here. So it's just moving the fault 2% of the line. And when you do this, you can see how the fault current changes as the location of the fault changes, which is pretty cool. So you can kind of get an idea of how the system will respond to faults along the line. And so you can intuit that when the fault gets further away from this terminal, this current should go down, and we can see that. And as we get closer to this terminal, this current should go up, and we can see that. So that's pretty cool. So I highly recommend you use that and play around with it, and you can kind of, it helps you get a better feel for what's going on in your system. So that's an intermediate fault. And then the intermediate fault with end open is just like the other one. It's going to run those same faults in the same steps with the other end of the line open. Okay. All of the rest of this is the same. So you can, again, you can combine any of these. Oh, I like this clear previous results tool. So we were stepping through all of these. If you don't want to have those anymore, you just say clear previous results. And now the only faults that will be shown are the ones that we select. So you can do close in with an outage. We can do a line in fault, no outage and with an outage. And we can do an intermediate fault, no outage and with an outage, 2 steps. And we can do 3 line to ground and single line to ground. And then we can do it with, what do we want our outages to be? We can do, say, these 2 lines. And there, boom. How many faults did we just run? We just ran 306 faults, and you can step through them all and see how the system reacts for faults at different locations. Oh, I didn't finish explaining these. So like this means it's the 3I0 current. This is the 0 sequence current, and that's what this button does. This would be the negative sequence current. You can also look at your individual phase current. So because this is a to ground fault, the A current is equal to the 3I0. So Aspen got that right. That's great. B current is 0. C current is 0. Hey, look at this. So you can, I mean, you can check homework problems and stuff potentially using this software. You know, you could put them, together a quick model and then run some faults and see what the answer is. So it's very easy. It's very quick. This this little clock here shows you the amount of time that relay will operate in. So this relay will operate on overcurrent ground overcurrent in 0.995 seconds for this fault. That's the relay that operates. And you can see it's going back. So this is an impedance, phase impedance zone 1, and that's going to operate instantaneously. So you can kind of watch and say, okay, well, at what point does the zone 1 stop operating? Still operating, still operating, still operating, still. Oh, there it goes. Now it's operating on zone 2 in 1.5 seconds. So these are cool tools to be able to see different aspects of the fault that you ran. You can also see this pictorially if you right-click on the terminal that you want to inspect, and you can do this show phasors and show the phasors in panel 1, and it'll give you the phasor diagram. So it'll give you the voltages and the currents for each individual fault, right? So this is an A to ground fault. This is a 3-phase fault, and it gives you all the voltages and currents at that terminal and the apparent impedance. So pretty cool. This is really helpful when you're trying to recreate a real world fault, and you can come here and run it and see how it compares with, say, a ComTrade file or an event report from a relay that tripped, and you're trying to determine, well, did it do what it was supposed to, or what happened? This is something I really enjoy doing, and coming back and trying to recreate faults using Aspen one-liner. Okay. So I included all these slides so that you can, like I said, go and do this yourself. I'm recording. Have a good night. So yeah. All right. So now we're going to get into coordination. How long? I've been going for a half hour. Okay. So now we're going to get into actually coordinating elements, right? Now we know how to model all of the equipment. We know how to run the faults. Now, how do we tell that the relaying is operating the way that it's supposed to? Before we get into that, I just want to define some terms because I'm going to be using them quite a bit here. So relay coordination is basically relays coordinate when the appropriate or in zone relay trips and the backup or out of zone relay does not. And there is sufficient safety margin known as the coordination time interval. Downstream is a relative term. It doesn't necessarily mean like in a radial line that only goes from point A to point B and everything is downstream. Downstream means closer to the fault. Okay, and then the upstream would be further away. So say the fault is over on this line and we're checking coordination between this relay and this relay. The downstream relay would be this one because it's closer to the fault, and the upstream, the one we want to operate slower, is this relay. So that's the difference between downstream and upstream. Local is similar. Local is referring to the bus that you're discussing, right? The point of discussion. So if we're analyzing the relay settings here, then this is going to be the local bus, the local relay, and then the remote bus would be over here at Kansas. And remote is a little bit more tricky because sometimes the remote relay is like, if it's part of a pilot scheme, what you're talking about is the relay at the other end of the line that's looking back towards you, right? This is the local relay. And you're talking about a pilot scheme and you're sending a DTT to the remote breaker or whatever. Might be this breaker that's at the remote end of your line. Or you might be saying the remote bus that's, the remote relay that's downstream of you, because that you're coordinating against it. So remote can be relative. It just depends upon the context of what you're talking about. But reliability and security. I think you guys have probably seen this before, but I like to think about reliability and security in terms of absolutes. So reliability is the likelihood that you will trip when you should. And so if you set your trip equation to 1, then your relay is always going to trip. So you can try and put it in service, and then it's going to trip right back out again. It's not very good protection, but it is 100% reliable, right? Whereas security is the likelihood that the relay won't operate when it shouldn't. So if you set the trip equation to 0, then the relay is never going to operate. Not very good protection. In fact, it's no protection at all, but it is very secure because it's never going to misoperate. So I like to think about reliability and security in those terms. And what we want is something that is both reliable and secure. But sometimes in order to become more reliable, you might lose security, and in order to increase your security, you might have to give up some reliability. So everything that we do is kind of a balancing act between the two. OOS is an acronym that stands for out of service. You'll see that in coordination studies a lot of times. It just means the device that is, well, it's out of service. It's not it's not contributing to the fault current. It's taken out for whatever reason. But if you see it and you don't know what it means, it can be confusing. So I wanted to bring that up. The CTI, we just covered that a second ago, but that's the coordination time interval. The minimum CTI can vary depending on your application, industry standards, client standards, etc. The CTI is intended to account for modeling errors, which, as we talked about, is very common. Luckily, you guys have had these classes now, so you're not going to make any modeling errors, so you can forget about that. But there are other errors that are present that could happen. There are CT errors, CT inaccuracies, relay errors. The relays have their own tolerance. Disparate relay operate times, and what I mean by that is different manufacturers and even different models may have different operate times. So a GE relay may have an operate time of 1 cycle for a zone 1 element, and the SEL relay may have a 2 cycle operate time for the zone 1 element, something like that. So you want to account for the different types of relays that may be in the system. Breaker operate times. Maybe the upstream breaker is a 3 cycle breaker, but the downstream breaker is a 5 cycle breaker. So there's 2 cycles of margin that you're losing there because of the different breaker operate times. So trying to kind of combine all of those potential sources of error, how would you even calculate that? Generally, you don't. Generally, you go by kind of the industry standard or client standard, and usually it's a client standard because they know kind of all the different parts and pieces of their system, and they've developed over time a feel for what the appropriate CTI is in different situations. If you don't have something like that, there's an IEEE standard. It's called the Buff Book. It's 242-2001, and it has this handy table that gives some generally recognized coordination time intervals. The ones that I use most often is between digital relays of 0.3 seconds, electromechanical relays of 0.35 seconds, and then fuses. It's usually clear space. And what that means is that because the fuse is already kind of in a range, right? We talked about how you have the minimum melt and then the total clear. The fuse can operate anywhere inside of that hatched area, but it shouldn't operate before the minimum melt, and it shouldn't operate after the total clear. So it's kind of already got a built-in margin. So usually your margin with a fuse is clear space because the fuse already has that margin built in. All right, overcurrent coordination. So now we're going to get into the fun stuff. So we're going to start over here at this relay. And what we're going to do is open up the relay group, and we're going to select the recloser's phase overcurrent element, and we're going to hit this button that says show curve, and it's going to open this new window, and it's going to plot the curves. And we talked about how reclosers have a fast and a slow curve. So this F means this is the fast curve, and just the one without the F, this is the slow curve. And you know it's the fast curve because on, well, let me start here. The x-axis is the current, and you can see that this is a log scale. It goes from 10, 100, 1,000, 10,000. So that's a log scale. So is the y-axis, and the y-axis is time. So when you'll hear people say we got to get the curve under that. What they're saying is that the curve needs to be under it on the graph, which means it needs to be faster, okay? Or it has to be above it, which means it needs to be slower. So you might hear people refer to that. I'm sure I do it all the time, but that's what is being talked about there. Under means faster. And this is why, because of this graph plot. So you can see that for the more current you get, the relay operate time goes down. So for, let's see, what's here? This is 3,000 amps. You get an operate time of 0.07 seconds, right? But for, let's say 1,000 amps, you get an operate time of 0.28 seconds. So I'm doing that by holding the click button and then just moving the mouse around, and it'll give you the X and Y coordinates. But generally, all relays and protective devices will have this kind of curve shape where they start up over here somewhere and then they go down, and they may go down faster or slower or have different shapes. But generally, they all kind of do this this general direction. Okay. So this is what that plot looks like. And I wanted to walk through this. We'll do it mostly in Aspen one-liner, but all the slides are here so that you can do this for yourself and play around with the faults and see what happens. And that's really beneficial. I certainly encourage you to do that. So I wanted to give you all of the steps we're going to follow in these slides. All right. So the next thing we want to do to check coordination is add another curve, because we have to do coordination between two curves. So we're going to add the fuse that's at the high side of this transformer. So what we're going to do is we're going to check to see if there's a distribution fault. We're pretending this is a distribution line, but if there's a fault out here on this line, we want this to operate before that fuse. Okay. And I actually had written down some questions that were asked last year that I thought were really good. And this one was from Paul, that he said, even if these don't coordinate, why would it be bad? Because the only thing you're losing is this transformer, and no additional customers are out, right? So I gave him two answers, the first two that jumped out to me, which was selectivity, which is really important. So if we have a fault here, we want this to operate first because it helps with restoration after the fault. So if somebody were to go out here and try and figure out what happened, they would see that if this fuse blew first, they would see that the fuse blew and then assume that the problem might be in the transformer. Transformers are really expensive, and it might be difficult for them to find the fault in the transformer. Obviously, you might have to do an inspection or whatever, right? So it's going to be a lot harder for them to isolate the fault, right? There might just be a tree on the line out here somewhere that they could clear quickly and then get everybody back in service. But if they have to figure out if the fault's in the transformer or on the line, that's going to be a problem. And then the other answer I had was single phasing of customers. That's just a quirk of fuses, because the fuses are single phase elements. So if you had a fault here, a single phase fault, it would actually only potentially blow one fuse on the faulted phase. And then three-phase customers may have poor power quality, to say the least. So you want to avoid that if you can. The recloser is probably a three-phase device, so all three phases would open and you're going to have that customer power quality problem. But I should have also said that fuses don't reclose. And so if this were a temporary fault, the recloser gives you those opportunities to restore power to everybody without having a prolonged outage if it was a temporary fault. If the squirrel got burned off and he's gone, Well, now we can restore power to everybody. So fuses don't reclose. That's another problem. And then I should have also said the longer restoration time, which I just kind of covered here, but somebody has to physically go to the site and, get up in there, into the truck maybe and replace the fuse, even if they found the fault, say, on the way to the substation, they still have to replace the fuse in order to re-energize it. Whereas if they had found the fault on the line, they could have just closed the recloser. So anyway, I wanted to cover that because I thought that was a really good question, and I think those are good things to keep in mind. So we really want to make sure our coordination is right between this recloser and this fuse. So there's two ways to add the other curve. We can do the add button, and then we can go to relay curves. And I don't really like this way because like I just said, I don't really enjoy this nomenclature, and it's hard to kind of figure out which of these is the right curve to add. So what I do is I go to the one line and I go to the relay group. I know I want to coordinate with this fuse, and there it is. And then I can just do show curve, and it'll ask me, do you want to retain the existing curves in the overcurrent curves window? And I just say yes. And so now it'll add that. And I asked this question last year because it was a live class, but I want to ask it again. You can pause the video and think about it, but does this coordinate? Okay. Having assumed you've paused and come back and had your answer, the answer is no. And if you're just looking at this graph, and it actually does, but we'll go over why it doesn't look like it. Okay. And the reason it doesn't coordinate, if this were the true coordination plot, is that the fast curve operates before the fuse, which is what we want. But as we talked about, we have a couple fast shots maybe, and then a couple slow shots. Okay, so you're going to do two of these, and then you're going to do two of these, say. I think that's what this is set to. Yeah, too fast, too slow. Okay, so once it gets onto the slow shots, now the recloser is going to operate up here, and the fuse is going to blow before the recloser goes on the slow shot. So now you're in that situation we just talked about where the fuse is blown for a line fault, and this is bad. But what this currently doesn't take into account is where what the fault current is and the relative current seen by the two devices. What do I mean by that? Let's say it's a three-phase fault on this bus. Okay, this relay is going to see 3,269 amps of fault current. But because the fuse is on the high side of the transformer, and we have the inverse of the turns ratio is going to be this current times the inverse of the turns ratio is going to give you this current because of the current being reflected through the transformer. So the fuse only sees 817 amps, whereas the recloser sees 3,269. So they see different amounts of fault current. And this is where, keeping in mind what your branch currents are is really important. It doesn't depend upon the total fault current. It depends on what the device sees. So now you've got these little dots on the curve, the plot that shows you where on the curve the relay operates. Okay, but this still doesn't mean much to us, this dot's up here. It still doesn't look like it coordinates. What you need to do is go to this show relay operations for one fault, and it will list all of the different faults that you have. Okay, and then you want to select this horizontal shift, and I like to align with curve 1. Okay, and the reason I do that is what I do is I add the curve that I want to operate first. I make that 1, and then the curve I want to operate second, make that 2, and then now what do we want to operate first? This one, and this should be slower. And so now you see it shifted that fuse curve based on those relative currents, which are listed here. Okay, and now you can see that it actually does coordinate. So this is great. The recloser will trip on the slow curve in about 0.2 seconds, and the fuse will blow on the minimum melt in about 1.2 seconds. So we've got about a second-ish of CTI between these two devices. So if we were coordinating with something upstream of the fuse, remember we talked about this, we can go here, we can double click on this, change it to total clear, and now it'll give us the total clear time, okay? So the other thing that you can do to help kind of figure out what the CTI is you can add a time difference slider. I'm going to remove this one just for clarity. No, that's what I want right there. Yeah, just one. So now you can grab this and it'll show you the CTI, the difference between any two curves. And you can align that with your fault current. And now you can see what the difference is, 1.277 seconds. So if you did that math, that's roughly what you would get. You can't get it exact because of the you can't get it right to the pixel, but it'll give you a very good approximation for what the actual difference is. And now you can see that this dot is on the total clear time. I want to change that to the minimum melt. Change that back and you can see the dot jumps down. And so we have 0.961 seconds. That's our CTI between these two devices. Okay. So this is looking great. But what happens if there's a system contingency? Okay, so now this is where you would run different faults. Maybe we run some interim faults here. Maybe we run different types of faults, and we want to do let's do intermediate, and we'll do it with some outages. Okay, and we'll take these lines out one at a time. Okay, and now let's see what happens. Now you can use this browse fault thing, just like we did on the one line, to go through the different faults. And you can see the current jumping around there as the faults oscillate between 3 line to ground and A to ground faults, right? And we're increasing our percentage of the line impedance where the fault is. And now you can see that you can figure out what your worst case is, right? What's the lowest CTI? Obviously, as these curves are diverging, as they're going up a log scale, we're getting much bigger CTIs as we get lower and lower fault current. So what I would be looking for, having observed that, is looking for like the maximum amount of fault current that both of these devices would see, or even better, the maximum fault current that this fuse would see while this is seeing the minimum amount of fault current that it would see. And that would tend to squeeze those down, that would shift them together. We don't really have a good outage that we can take that shows that. But let's go back here, and because this is just stepping down the line, let's go back and do a bus fault again, and we'll just do it with outages so I can show you the difference with the different outages. Okay, so now we can go back and we can again go through. What's this CTI? I think that's our worst case right there. And now we can see if there are any that plot to the right of that. Oh, look at that. So that's actually a lower CTI, okay, for a double line to ground fault. Oh, excuse me, with this line out of service. So a 3 line to ground fault with this line out of service. That gives us a lower CTI. So now this is our new worst case. So we can keep scrolling through the faults and see if we can find any that give us a lower CTI. And we don't find one. So now we know if we've ran all of the possible contingencies that we may want to consider, we know that this is our minimum CTI. This is our worst case. And usually what you do is you don't include every plot that you run. You just include the worst case, and you say that this is the worst case CTI. And because this CTI is greater than, well, in this case, the minimum CTI is just clear space, you can say this proves that these two elements coordinate. You'd want to be more thorough in your approach for which outages to run than we just were. I just kind of picked some, but that's generally what you do. And I like to run all the faults, even if I think I know what the worst case is going to be, because sometimes you're surprised. And especially early on in my career, doing it this way, I learned things, because I would things would happen that I wouldn't expect. And then I would go, oh, okay. And I'd kind of look at the model and I'd kind of figure out, okay, I see why that's doing that. There's a loop over here. And all right, that makes sense. So I like doing that. Even like I said, to this day, I still do that. I think it's the best method to make sure that you haven't missed something. And I think it's a great learning tool. So I want you all to, there's no homework problem on it, but please do it anyway. I think you'll learn a lot from this exercise. So try this coordination, run faults, see what happens. If this didn't coordinate, a cool tool is to right click and do the trial adjustment. Okay, and actually let me add another curve that's not relevant to this coordination, just so you can see this better. This ground relay. So I'll say, yes, I want to add it to my curve. So this is the plot for this ground relay. And you can see this vertical line here. What that is, it is the instantaneous element, okay? And as soon as it's set to 2000 amps, and as soon as you get above 2000 amps, the clearing time goes to 0, okay? That's why it's shown as a vertical line. Well, I'm going to get rid of that instantaneous element just for the purposes of our discussion here, because I wanted to show you the trial adjustment. If I right click and do trial adjustment on that, it'll give me all of the ranges that this relay can be set to. So it's currently set to a pickup of 1 and a time dial of 0.5, and it's a CO5 relay. Well, what happens if I increase the pickup? Well, this will shift the curve to the right, like I had described last class, right? So you can shift it left and right, and then the time dial shifts it up and down. So you can see if this were our coordination plot, you can kind of use this and figure out, oh, what do I want my time dial to be? And you can kind of manipulate the curves and put them in a spot that's reasonable. And then you can do apply it. And now it changed the setting for that relay. And so now you can go do another coordination and make sure that coordinates, right? Maybe we slowed this down. So now we got to check one more upstream and make sure that it's still faster than the next relay upstream. So this is how you do these coordination studies. Okay. That is overcurrent relays. I've been going for 45 minutes-ish. Is that right? 45? No, 55 minutes. So I got 20 minutes left. Okay. Now we'll, well, let me flip through my slides here and make sure I didn't miss anything. So like I said, these slides go through how to do this step by step, everything we just talked about. Oh. And so you can do that on your own. And I really want you to do that. Oh, yeah, I should have done that. So now that we know that our relays coordinate, I'm going to add that back real quick. Now that we know our recloser and our fuse coordinate, you might want to know whether or not that transformer is protected, because what good is the coordination of the relays if the transformer is going to get damaged? So what you can do when you have these, once you have your curves on here, you can add a transformer damage curve. You can also do conductor damage curves if you want to look at the damage curve for, say, an underground cable or a transmission line. You can add those as well, but the theory is the same. So you go to the transformer damage curve, and it'll let you automatically select which relay you want, which relay is associated with the transformer you want to add the curve for. Okay, so it doesn't matter which one of these select. We'll select the recloser, and then or you can do a manual, I suppose, if you want. But it automatically populates the impedance. And remember how I said for transformers we want to have that MVA rating entered, even though it doesn't impact the fault currents. The reason you want to have that, apparently I have to close that window. The reason you want to have that in there is when you add your transformer damage curve, it takes this value, that ONAN value that we put in, So it assumes that that's the base rating of the transformer, which is what the damage curve is based on. The damage curve is a function of the Onan rating of the transformer and the percent impedance. So if I go back here and add transformer damage curve lined with the recloser, okay. If that wasn't in there, it would just assume that it's 100 MVA, and then it would give a 39.6% Z. So you like to have that in there because now it's associated with the actual transformer curve, transformer damage curve. Yeah. You can also add an inrush curve if you want. We'll talk about this more when we go over transformer protection, but when you first energize a transformer, there's a big inrush of current that decays over time, and you can plot that inrush, the expected inrush based on the size of the transformer and the percent Z, and then make sure that that's lower on the curve than your fastest relay, because you want if the curve came first, then the curve, the relay would trip before you got to the inrush curve. So it's showing how much current you should expect at each point in time along that curve. If the relay is under that, the relay is going to trip, or could trip. The amount of inrush current is dependent upon a lot of factors that it can be finicky. We'll get into that, but may trip for a particular fault. So you can add that if you'd like. So we can add this damage curve. The transformer damage curve is actually kind of like two curves. There's this body part, and then it's got the two little legs here. This is called the infrequent damage curve, and then this little leg here is called the frequent damage curve. And so what you want in general is for the fuse to be under at least the infrequent damage curve, and the recloser to be under the frequent damage curve. And why that is that faults on a distribution circuit, say, are way more common than faults in the transformer. And so we can expect that the transformer is going to have to see many or frequent faults out on the distribution system, and will need to withstand that, but it will see fewer faults on the transformer that the fuses will need to flow for. Okay, so it can see that amount of fault current frequently, and then this one infrequently. So that's why we want those curves to be under the damage curve. Okay, so now we can run our faults are already run. Good. So now we can just show for, let's say, this one, and we can make sure for all of our different faults that we ran that the transformer is protected, and it is. So that's good. This is just housekeeping. I'm going to skip it. Not enough time. You can add comments and stuff to your relay graph. That's how you would do it, and that's so that you can add details and annotations and stuff to the curve, so that somebody else looking at it can see what you did, and you can give it to the client, and they can give you lots of money. Distance relay coordination. Okay, I got 15 minutes. Spend 15 hours on this. All right, so we're going to select this, and we're going to go to a phase distance relay, and we're going to show this curve, and it's going to open in a new window. So this is a distance plot. I don't know if you've seen this yet or not, but if you haven't, this is what it is. This line here represents the impedance of the protected line. Then this first circle is the zone 1 element that we said is going to be under reaching of the remote end. Looks like this is set at about maybe 75% of the line impedance. The second line is the zone 2. So we can see that overreaches the remote terminal by, doesn't look like much. I'd probably want that a little higher, but I didn't set this. It was just in the model. And then it looks like they have another backup zone 3 distance element that reaches further out into the system. So zone 1 is set at 7 ohms secondary, 75 degrees. with 0 intentional time delay. And then the zone 2 has a ½ second time delay, and then the zone 3 has a 1 second time delay. So this is pretty typical of the distance plots, okay? Then what I can't do, even though I would really like to, is go to the line we want to coordinate with, double click it, and do show curve like we did last time. You can't do that when you're doing distance plots. And the reason is when you add a relay characteristic, I think it's this one. Yes, it's this one, which is this relay here. So we're going to check for faults on this line to make sure that this relay operates before that relay. That's what we're going to check. This is the coordination we're doing. Okay. The reason you can't just add the other curve is because you need this offset. And what the software automatically put in the impedance of this transmission line in here, right? And the next relay is in the forward direction, meaning they're both looking in the same direction. If it was reverse, it would be this, you might use reverse if you were putting this distance relay into the plot. That would be a reverse looking, right? Because they're looking at each other. Okay, so we're going to do a forward. Just want you to understand the difference. You might do this one versus this one to make sure that the pilot scheme works the way it's supposed to. That the blocking element is going to block for all faults behind it that are going to be seen by the remote end relay that's looking back on the line. That's why you would use that. Our coordination that we're looking at is forward. So it put in the transmission line impedance so that the other line is modeled here so that you can get a better representation of how these relays are kind of stacking up. Okay, so what I'm going to do is I'm going to split screen this. Okay, and I'm going to run some intermediate faults, 3 line to ground, on this line without an outage. I'm just going to start with doing 1% 3 line to ground. Okay. So now what we're seeing here is some. Oh, I didn't clear the previous faults. Got to get to the first one. Okay, here we go. So there's 2 boxes here, a red box and a blue box, and they're hard to see right now because the fault is basically right here at this end of the line, so they're both kind of covered, right? But as we move away, you can see that the boxes separate. And that's because the blue box is representing the impedance seen by the blue relay, that's this one here. And then the red box is representing the impedance seen by the red relay, which is back that way. And because of the in-feed here, and I'm sure whomever is talking about the line protection will talk about in-feed, but because of the in-feed, these don't plot right on top of each other because the blue relay is seeing the actual impedance between this terminal and the fault, and then this red one is just seeing the apparent impedance from this terminal to this fault. And the apparent impedance is higher due to the effect of in-feed. Hopefully somebody else covers that in greater detail, but just so you know, that's why it's doing that. So as we move away, what we're trying to do is make sure that these relays have a CTI that's acceptable, okay? And right now, this relay is, because it's in the zone 1, is operating in 0 seconds, and this one's operating in 1 second. So even if we start back here, first fault on the line right there. So the red relay is within that zone 2, right? And we kind of expect that because it's got to overreach this line, right? It's got to see out here somewhat because we want to make sure that it sees all faults on this line. And we're putting in the time delay for this scenario right here, right? So the blue relay is going to operate high speed. And then the red relay is going to wait for ½ second, okay? As long as the blue relay trips, then the red relay will stop seeing the fault and everything is fine and you've coordinated. If the blue relay fails, then the red relay will trip in ½ second, okay, and clear that fault. And hopefully all of the other terminals that are looking into this bus will see that fault, and they'll all operate if there's no breaker failure or backup relaying or whatever. But that's the idea of that backup. And that's probably what they had intended for this zone 3, right? So this is actually overreaching, it looks like, most of, if not the entirety of that other line, so that it can clear faults out there if the breaker doesn't open for some reason. Okay, and then as we get further away, those lines separate, and now the red relay is in the zone 3, but the blue relay is still in zone 1. So you're just checking to make sure if they have the same time delays, what you're doing is checking to make sure that they're never going to be within the same zone. So let's say that this relay had a zone 2 impedance of, instead of 10 ohms, let's call it like 14. Looks like that'll do it. Yeah, it does. Okay, so if this zone 2 were set to 14 ohms, now the red relay is in the zone 2, okay? And if the blue relay gets out of the zone 1, okay, it's out of the zone 1 and in its zone 2, they're both in their own zone 2, they're both set to a half-second time delay. That's going to trip at the same time. That's bad. That's not going to coordinate. So you lose both lines for a fault right there, if that's how that relay is set. So what you need to do as the protection engineer is either adjust that reach, or you need to increase this time delay. Okay, so that's how you check for distance relay coordination in a nutshell in 15 minutes. And with that, I have, what do I have? Like 5 minutes. Okay. I managed to get through everything I wanted to get through. I would also run this with outages and see the way that the coordination was with less in feed, because it'll tend to bring this red dot back, so it's more likely to be within that zone 2 reach still. So I would run it with each one of these elements out of service one at a time. Okay. Other questions that I got last year that I thought were good. How do you know what your worst case is? That'll depend on what you're looking for. So if you're looking for like a breaker rating, you want to get your maximum fault current, right? So your worst case might be with all equipment in service. With line coordination, it's a lot more challenging, because you might have loops. So this is probably hard to explain here in 3 minutes, but say we're coordinating this relay with this relay, okay? You would think, or at least I would think, that like in that last scenario, maybe your worst case might be the highest amount of fault current. If you take one of these lines out, like this line over here isn't even connected to either bus, but if you take, let's say the fault is here, no outage, okay, this relay sees 1297 amps of fault current, right? So if we take this line out, it's going to actually see 1211. Oh, okay. Well, let's take this line out. Now that generation will have to go that way. I think this will now be higher. Now it sees 1450. So you may be trying to, like, say we're setting an instantaneous element, and we don't want the element to operate instantaneous phase over current element. We don't want the relay to operate for a fault on this bus. So you might think that the worst case scenario is with the maximum fault current. So I would assume, well, that's with everything in service. Not necessarily. It depends on your network. And that was the point I was trying to make. It really depends. You got to play around with the model. You got to try things and see what happens, because sometimes when you intuit things, I know a client that has a standard that says to check when you're setting the phase instantaneous overcurrent element, to check the fault with all lines in service. Well, in this case, that wouldn't be your worst case if you're looking for security of that instantaneous element. You'd want to take that line out. Okay. So that kind of stuff, even if the standard says one thing, it may not actually be appropriate for your application. So that was a question I got, and I wanted to go over that. How do you know? It depends. You got to play around with it. How do you know which contingencies to consider? That's kind of the same thing. You gotta try a lot of them. One of the other things is that you want to. Sometimes the model isn't enough. Sometimes you need to have information about the system. Like, say this is a wind farm and this is a solar farm, which it looks like they are. Well, you might want to consider the fact that the solar farm is out and the line is out. And the reason being, well, the solar farm is not putting out anything at night. So is the solar farm being out of service really a contingency? I would argue that it's not. So you want to take that out and a line out, even though usually you only consider one contingency. Or maybe this is hydro and they generate in the spring when they've got the snow melt, and they don't have much in the late summer, early fall. So again, part of the year that's going to be out of service. Is this generator unit connected? Meaning, is the breaker here, or does the generator also have a low side breaker that when they take the generator out, they only take the generator out? Or when they take the generator out, do they take both the generator and the transformer out? Because this is a ground source, that can have a big impact on your ground overcurrent coordination study in the area. So it's really helpful to have an understanding of the system you're looking at and not just looking at the model, because just taking a single contingency, it's hard to tell what a realistic contingency is. Okay. All right. I'm out of time, and I think I covered all the questions that I wanted to cover. So I apologize for the brevity. I'll try to do better if I'm invited back to do this again. Call with any questions on the homework. Email me, give me a call, shoot me a text. I'm available, willing to help. Love to talk to the students and get to know you guys. So, all right. Have a great rest of your semester, and I'll see you for transformer protection. Thanks, everyone.